In this lesson, we're going to do a little bit of an introduction to piecewise functions. A piecewise function you've probably seen graphs of before. They tend to be these drawings of sort of like multiple curves on the same graph. So technically what we can describe it as is a function who is defined by different rules over different regions. And so they are typically going to look like this f of x on the right over here, where we see this big squiggly bracket and then a list of different functions and regions. So what this would mean is we have this like f1 function for any x contained in the first region A1, f2 for any x in A2, etc., all the way down to however many functions you have in your list. Some things to be mindful of. These regions on the right are typically intervals, as you can see in the example that I've given below. Sometimes they'll be like just a set point, but really the only restriction is that they should be sets. They should specifically be sets of real numbers. So maybe I'll write that down. Dots don't show up. And something else that you want to be mindful of is that you probably want them all to be disjoint. So what I mean is that you don't want to have any particular x value that shows up in more than one set. Just for example, let's say x equals 2 was in both A1 and A2. Then what that would tell you is that you're supposed to use both f1 and f2 as your rule. And if you remember from the definition of what a function is, you don't like two different things. So the only way that that would actually work is if like f1 of 2 and f2 of 2 are actually the exact same output. So you're kind of playing with fire there by having that overlap, and that you need the outputs to actually match. Otherwise, it's not going to be a function. So you probably want absolutely no overlap with any of those functions. If you look closely at the function that I've written here on the left for my example, you will see that there is actually no overlap. We do have these intervals. The first interval, maybe I will label them all A, B, C. So the first interval includes -2. We can see -2 in the second interval, but it's not actually included in that interval. Remember, it stops just at -2, but doesn't actually include it. So there actually is no overlap there, which is fine, which is good. It's actually what we want. All right, so yeah, we'll go through and solve this. So what we'll do is look at x is -3. So the first thing that we want to do is figure out what region that actually occurs in. So x is -3, so this means that x is in A. And the reason is -3 is inside of that interval, everything less than -2. So less than or equal to, technically. And so because it's A, what that tells us is that we use the corresponding rule of 2x plus 3 when we want to actually evaluate what the function does. So f of -3 is going to be 2, and then my x, which is -3 plus 3, that'll be -6 plus 3 is -3. So that should be my output there. All right, I don't even look at the other rules because those might generate other values, and those aren't the values that I use for -3. I follow the rule that matches my interval. And then we'll do the same thing for x is -2. So you have to be a little bit careful with this one because it is on the edge of the two intervals. But this one is also in A. I mean, since -2 equals 2, but we can also say -2 is less than or equal to itself because of the or equal in that statement. So it's in that region A. We're also going to use the same rule, 2x plus 3. Right? So we'll use the same rule. Now, notice we can't say it's in B because I can't say that x is strictly greater than -2. -2 is not greater than itself. So it's that or part of the inequality that helps us out here. And so I'm going to have f of negative 2 is 2 times negative 2 plus 3, and that one will give me an output of negative 1. All right, f of 0. So that one's not too hard to find. It's a little bit more clear since it's not on an edge. So this is in B. Since negative 2 is less than 0 is less than 2. And so that means that we're going to use the x squared rule. And so what we'll do, we just plug in f of 0 is 0 squared equals 0. And so I've got maybe a couple more sort of weird things happening here. And x equals 2, what you'll actually notice is x equals 2 is not in any of the intervals. It's just on the cusp of B, but it's not in B. And it's certainly not bigger than or equal to 3. It's certainly not smaller than or equal to negative 2. So it's not in any region. So what we're going to have in this case is there is no output. So f of 2 does not exist. That's it. There's no rule for it, so it doesn't exist. It wouldn't have a point on its graph. And then finally, f of 4. So this one occurs in C. So we're going to use the 1 rule. And so this one tends to kind of trip people at first, but it's actually pretty straightforward. It's going to be f of 4 equals, it's actually just 1. There's nowhere to plug in x equals 4. It actually is just 1. It's a constant 1. It's constantly 1. Yeah, so that's how we get those inputs. We'll talk next about how we would do some graphing these piecewise functions. So one method you can sort of always use to graph is just figure out a bunch of points and plot them. I wouldn't really recommend it for these piecewise functions because it's maybe a little bit harder to see patterns when there's, in this case, 3 different patterns. We also can see that there's a gap between 2 and 3 that you'd want to be mindful of. And so there's actually just a little bit too much to keep track of to just plot a few points and connect the dots, because you have to use a different rule for every section. So instead what we'll do is just use a little bit about what we know about graphing to try to graph these things, and hopefully that puts a little bit of a better picture together for us. So I shouldn't give you any like crazy functions in there to do, hopefully simple things that we sort of remember how to graph.